Your modern CPU is tearing through a massive AVX synthetic workload. It's pulling heavy wattage, executing the math, and then the clock speeds suddenly plummet. You check the telemetry expecting a thermal throttle, but the CPU die temperature is sitting at a perfectly safe 65 degrees Celsius. Your cooler is executing its job flawlessly. The silicon is fine, the cooler is fine. The bottleneck causing this performance drop is the Voltage Regulator Module, the VRM. Before power reaches your processor, the VRM must intercept the 12-volt rail coming from the power supply and aggressively step it down to the precise 1 volt to 1.5 volt range the silicon actually uses. This is a monumental task. Today's flagship CPUs demand extreme amounts of current at that low voltage, frequently pulling well over 100 amps under full load. You cannot judge a motherboard's ability to handle this load simply by reading marketing spec sheets or counting the number of power phases printed on the box. Delivering stable power requires balancing two competing forces: maintaining a rapid electrical transient response to feed the CPU instantly, while simultaneously managing the extreme heat generated by that switching. To locate where system stability actually breaks down, we have to trace the exact physical path of an electron, from the power supply, across the motherboard PCB, and directly into the CPU. The journey begins at the top of the bare motherboard PCB, exactly where the 8-pin EPS power connector anchors to the board. The 12-volt current flows to the absolute brain of the VRM ecosystem, the pulse width modulation, or PWM, controller. This chip dictates current timing. It sends out a digital square wave, instructing downstream power stages when to open and close. The speed at which this controller turns those power stages on and off is called the switching frequency. On modern boards, this typically runs anywhere from 600 to 1000 kHz. Pushing that frequency higher yields a major electrical benefit. It dramatically improves the system's transient response. When a CPU wakes up to render a bursty, cache-heavy workload, it asks for dozens of amps in a fraction of a millisecond. A high switching frequency allows the VRM to react to that demand almost instantly. By reacting quickly, the VRM prevents the CPU voltage from dropping below the stability threshold, keeping the processor from crashing during those violent workload shifts. This chart illustrates the core engineering cost of that speed. As switching frequency increases along the bottom axis, the thermal output on the vertical axis curves sharply upward into the red danger zone. This happens because the MOSFETs spend more total time in a transitional, high-resistance state between fully on and fully off. Spending time in that high-resistance zone generates exponential heat output, destroying overall electrical efficiency. Tuning a PWM controller is an inescapable compromise. You are constantly balancing the need to prevent CPU voltage droop against the risk of a motherboard thermal meltdown. Following the signal away from the PWM controller, we arrive at the physical array of MOSFETs surrounding the CPU socket. Traditional discrete layouts use separate high-side transistors, low-side transistors, and a driver chip. Modern boards merge these into a single package known as DrMOS. Consolidating the silicon reduces the distance current travels, minimizing parasitic inductance and increasing power efficiency. The most advanced versions are called smart power stages. These are DrMOS units equipped with built-in sensors that feed highly accurate current and thermal telemetry right back to the PWM controller. Understanding these individual stages exposes the primary myth pushed by motherboard marketing materials: phase topology. Manufacturers frequently use intermediate chips called doublers. These chips take a single PWM signal and split it, artificially inflating the advertised phase count so a board can be marketed as having 16 phases. The fatal flaw of a doubler is that it introduces physical signal delay into the control loop. It takes time to split that signal. Compare a bloated, doubled layout with a true direct 8-phase VRM that utilizes high-quality 110-amp smart power stages. Because there is no doubler intercepting and delaying the instructions, the true 8-phase setup dynamically responds to CPU transient spikes significantly faster. When pushing a CPU in extreme overclocking scenarios, fewer, smarter phases using DrMOS silicon will consistently outperform massive banks of cheap, double, discrete components. As the raw, erratic current exits the power stages, it directly hits the inductors, components more commonly known as chokes. The inductor's core job is to physically resist sudden, violent changes in electrical current, acting as a heavy shock absorber for the power delivery. Overclockers look closely at two specifications here: DCR, or direct current resistance, and ISAT, the saturation current. If peak CPU loads exceed that saturation current rating, the choke experiences soft saturation. It loses its inductance, causing the voltage ripple to balloon entirely out of control. If the choke holds, the smoothed current passes through and hits the final filtration stage, the capacitor array. This diagram shows the waveform entering the capacitor bank. These components act as bulk energy storage tanks, flattening out the remaining jagged voltage ripple into a perfectly flat, clean DC line. Different grades of capacitors handle different parts of this job. The large cylindrical ones are solid polymer electrolytics. These polymers provide deep bulk storage capacity and maintain incredibly low equivalent series resistance across operating temperatures. Directly behind the CPU socket, you will find tiny arrays of multi-layer ceramic capacitors, or MLCCs. Placed close to the silicon die for their extremely low equivalent series inductance, they absorb the highest frequency transient spikes right before they penetrate the processor. Together, the heavy chokes, the bulk polymers, and the rapid response ceramics form a comprehensive filtration ecosystem. They ensure the CPU receives only pristine, ripple-free power. Stepping back from the microscopic component level, we have to look at the entire CPU socket area within the physical reality of your computer case. All the electrical inefficiencies we've traced, switching losses in the MOSFETs and resistance inside the chokes, translate directly into physical heat radiating off the motherboard. This creates a destructive cycle inherent to MOSFET operation, known as a positive thermal feedback loop. As VRM components heat up, electrical resistance increases. To push the exact same current through that higher resistance, they generate even more heat, accelerating the cycle. Motherboards have a hard-coded safety mechanism for this. Once the VRM thermal sensors detect temperatures crossing roughly 100 degrees Celsius, the system intentionally throttles the CPU frequency to prevent a catastrophic hardware fire. This brings us to the convection conundrum created by modern all-in-one liquid coolers. A liquid cooling block replaces the traditional downdraft air cooler. While it keeps the CPU perfectly chilled, it entirely robs the surrounding VRM components of vital incidental airflow. If pushing high phase amperages without direct airflow, massive, heavily finned VRM heatsinks connected by heat pipes are strictly required to diffuse the thermal load. You can install the most perfect, but if it is starved of convective airflow, it will invisibly throttle your system's performance. When a high-end system runs flawlessly under extreme stress, it isn't by accident. True overclocking headroom demands a perfectly tuned PWM controller, integrated DrMOS power stages rated for massive sustained amperage, heavy inductors that refuse to saturate, and ultra-fast capacitors. And that entire electrical path must be continuously protected from thermal runaway by sufficient heatsink mass and directed case airflow. To build a truly stable system, look past the marketing phase counts. Read the component data sheets, evaluate the physical heatsink design, and follow the power. This information is brought to you by Microdyne Computer Services. If you like this content, please consider giving it a like, subscribe, and feel free to comment. It helps our tiny little channel grow and be seen in searches. Please stay tuned as we soon transition from AI to live videos. And as always, thank you so much for watching.